Hello, good afternoon. I'd like to talk about the pavement evaluation procedure. Okay, so this is the continuation of the road maintenance. Um, the purpose of the pavement evaluations. Okay, so for the roading authority, whether it's in NZTA or the city council, the district council, okay, they all have their own the procedures. Okay, so the purpose of the pavement evaluation is that um, they have three main purposes. Okay, listed in order of increasing detail. Okay, so they have this network level and project level. So the network level is the medium to long term planning, and the project level is short term planning. So when they do the evaluation, whether they do it for the present, the short term, for with the intention to do some like routine maintenance, periodic maintenance, you know. But the plan, if they want to plan for longer term, medium or longer term, they will need to go for the network. And also for the pavement evaluation, they have to do some research as well, research on the pavement technology. So they will need to do some like testing, sampling, all those things. Okay, on-site testing and the lab testing. Okay, so the network level surveys are used in pavement management, enabling less precise and long-term predictions of maintenance needs for pavement throughout the whole of a road network. So they will need to do some survey um, uh, for the whole network. For example, in Auckland, the Auckland Transport, they will need to choose, let's say, certain roads to do the survey, and they could do they cannot afford to do all the areas, all the whole length of the road. They might need to choose just a sample of the road, okay, to do the survey, and they could do it on foot, so for, let's say, for a stretch of road which is not too long, or inside the vehicle. Okay, so um, so they sometimes they just call it the visual survey by vehicles, or we just call it the windshield survey. Okay, so this is a network level surveys which with the intention for the medium to long term planning. Project level survey is evaluation of existing pavement for the purpose of planning and designing maintenance and rehabilitation treatments. This one is more like a short term survey for the uh, for the maintenance, for the routine maintenance, for the preventive maintenance on the road. So this something that they need to do it to rectify any repair on the ground. Okay. In a maintenance context, the main aim of project level pavement evaluation is to identify the precise mode and cause of failure and or excessive deterioration. So if you have an area with some failure, whether it's extensive patch of cracking, crocodile cracking, or block cracking, or certain place there's some this one this excessive settlement of the rods. The rod is sinking, so it could be the pavement materials which has some failure, or maybe there's some movement in the subgrade. The subgrade is giving way, so need to identify it. If you can't do it by visual observation, you might have to do the like testing, like Insitu testing, or do some coring and then bring back to the lab for to be studied. Okay. Pavement evaluation should be designed to provide the necessary inputs for the selection and design of maintenance treatment. So we need to have some sort of data, okay, from the site to bring back to the office and to be studied, to be discussed, to be brainstormed, and then to provide the necessary to decide on what are the best necessary treatments for all the defects. Okay, pavement evaluation methods. There are a number of different methods of assessing the condition and maintenance need of the existing pavement. Okay, so how do we? There are different methods of doing the evaluations. Four of them. First one is sampling and laboratory or in-situ testing of existing subgrade and pavement materials. So this one you need to collect sample from the site, and then you do some testing like CBR testing. You do the moisture content testing and so on, in the like liquid limit, partial limit, so on. Or you can do the testing on site, like in-situ testing, the CBR testing of the rod, which we show later on. Okay. Secondly, visual inspection, where the observations are made and recorded by trained inspector on foot. So the inspector will need to go to the site, you know, to check the site condition, to find where are the defects. You know, they need to measure, they need to find the location as well. Previously, you know, they have to mark, I think they have to mark it, you know, the chainage of the rods, and they can they can identify where are the defects, you know, and then they can see the cracks, the depression, the rutting, and they can measure the cracks as well. Okay, so this one is by the trained inspector. There may be a group of them. They go to the site, and then they need to do the inspection, and then they need to record down in the form. Okay, I think we just look at the form. Where are they? There's some sort of form, you know, they can later we'll look at that as well, look at this as well. So they need to make some sort of records on the defects on site. Okay. Okay, so that is the visual inspection, which is done on foot. And thirdly, visual inspection from a moving vehicle. Observations made by trained inspector, desirably in the front passenger's position, or by video or subsequent interpretation of both. It's called visual inspection from a moving vehicle, or it could be just say it's called the windshield methods. Okay, just you look to the front windshield, and then you can look at the defects. But usually it's recorded by like a video to record it, and then the GPS as well to locate the position. So the people sitting in the car, in the passenger seat, and they have all the monitors, you know, to look at it, and then they have the video as well to record it, you know, and then they have the GPS to locate where are the position. They can input it manually as well, you know, where is the place, at what point, you know, this if they spot potholes on the road. Okay, but nevertheless, this method is not as precise as the visual inspection on foot, because this vehicle is moving quite fast, so it's less precise than the inspection on foot. Fourthly, automated survey of selected pavement condition parameters and combinations of the above. Okay, so this one, certain things that cannot be done by the eyes, observations. For example, you can, it's hard to record, for example, the strand of the pavement, the routine. There's so quite extensive routine. Maybe it's running kilometers and kilometers, and then you just can't possibly you record it by observation. So they need some sort of machine, machine mounted mounted on a vehicle that can record it. Okay, so yeah, I will show something about it, and later on we will show more on this the automated survey. I need to close it down. Actually, I need to go straight. Need to go to the this one, the pavement data collection.
Their toll on our streets every day.
We really want to find out what's going on with our roads and throughout the city of Arvada.
So the city hired Atkins Engineering, which teamed up with a company called Cartograph to assess our streets.
It's meant to collect all the distresses on our streets to determine what kind of distress each street is. Where does the street rank from 0 to 100? 100 being the best and 0 being the worst.
The 2015 pavement inspection is a follow-up to one taken in 2012. In that go-around, Arvada streets averaged a score of 62.
With this year's program of collection, we're going to compare the two and determine where are we falling short on and where are the areas that we're actually gaining, and where can we average this out to actually help improve the city streets.
Cartograph's vehicle is outfitted with sensors that collect data as it moves along.
You can see the red light, the lasers that's shooting down onto the pavement. It measures a longitudinal profile, which gets the inches per mile of roughness, as well as wheel track rutting.
Along with automated measurements, a crew inside the truck collects data through visual inspections.
If we see a pothole on the other side of the road, we can log that as we travel past it, so it gets the exact location, both from a GPS standpoint and from a distance standpoint from intersections. So the city will then know exactly where all the pavement defects are.
They'll enter in, how many cracks there are in a certain distance, what type of pavement there is, whether they're on concrete or asphalt, and where that changes.
The screen up here is capturing and logging all the sensors that are being collected on the front bumper.
Okay, so that survey there's it's a mixture of I think it's automated survey. They have this the laser shine beam on the ground, which can actually can do quite a lot of can study can record the profile of the road as the vehicle move along, or it can actually is the C is a visual inspection by moving vehicles. It can record any defects on the road. So so that's how they collect the data, pavement data collection. So on the vehicle they can do actually the windshield observations, or the automated this one, the surveys, to test the routine, to test the roughness, which is the texture of the surface, to check the strength as well. Okay, we need to look through the different parts in slightly more detail. Sampling and testing. Okay, so this, which is the the first one, the sampling sampling in laboratory or in situ testing. So a detailed investigation may be warranted before an expensive treatment such as extensive patching or pavement rehabilitations, especially if the cause of surface failure is in the lower pavement cost or subgrade. So if it's a simple pothole, probably you don't need to do much investigation, like you don't need to do some testing for that. But if there's something, you know, this is which not immediately sort of apparent what is the cause, you know, because something that, let's say that part of the rod is sinking, we don't know what happened to it, and certain part there's extensive cracking, you know what happened to it. So that one it might warrant to have laboratory testing or in-situ testing, so that if they need to they can do the site testing, or they could do it, they could collect the sample back to collect the sample and send it back to the lab for testing. Okay, let's look at the collection of chlorine sample. So this technician drilling through the rod surface. This is a completed rod with the pavement, the sub-base cost and the wearing cost. So he's drilling through the pavement to collect a sample. Okay, so that's a collection of sample, collection of chlorine sample from the site. Field sampling and testing are normally designed to determine the adequacy of cover above the subgrade, field moisture condition, and the suitability of the existing base material in the proposed pavement structures. So those samples actually can determine, you know, whether the pavement is sufficient, the pavement thickness, the pavement layers thickness, whether they are sufficient, you know. So whether, you know, the chlorine could drill through the wearing cost to see that, you know, whether it is whether it is fulfilling the design, from the design, you know, the design said that it's 150 thick, whether that wearing cost is it 150 thick, you know. So, and if it's sometimes they have this deep lift best cost, that means that it is they have a soft in-situ stabilization with the cement, you know, or with the bitumen. They can drill through as well, and they collect the sample, see how whether it satisfies the thickness criteria. Okay, typical tests including cost, thicknesses, moisture content, fuel density and grading, Alterberg limits. This is, I think, it's a liquid limit, and CBR field or laboratory of the various layer including the subgrade. So they can do the different type of tests, you know, the cost thickness. Just now I think the one is they drill through a sample, they can check the cost thicknesses. The moisture content, they can get a sample. It should be like they take the sample of the best cost or the sub-base or the subgrade, and then bring it back to the office. You know, they need to drill through and collect the sample, and check their moisture content, and the fuel density. They can check the fuel density as well, and grading from the sample. They can check the grading, and the CBR test, they can do it on site or at the lab, in the lab. So if it's in the lab, they need to get the sample back to the lab for testing. But let's see how they do it on the Insitu CBR test.
This time we're going to demonstrate Insitu CBR testing, which is an empirical measure of ground strength normally used for road design. So for this test we need a reaction load, some sort of dead weight to use, and for Insitu CBRs by the British Standard Method we're going to be using our vehicle, this pickup. The axle stands rather, will release the pressure and then hopefully the vehicle will rest neatly on top of the axle stands. With the jack down, we can then move that out of the way and continue with the assembly. And as you can see, the vehicle, the rear of the vehicle has been jacked off, so the rear wheels are just about clear of the ground. That we'll be applying, and there at larger gauge is a penetration gauge which will measure how far the plunger is penetrating into the ground as we wind that handle there. And on the bottom we have two surcharge discs as well. So the only thing we need to do now is set up the datum bar. So we pop the datum bar into position. So as you can see, we've applied a preload of around 40 newtons, which for our proving ring works out a load of about 250 newtons, which is the appropriate preload for a CBR of over 30, which is what we're expecting. So now we are fully assembled. The intent of the test then is to wind that plunger into the ground so it penetrates at a rate of approximately 1 millimetre per minute. So this is the actual plunger. As you can see, it's a hardened steel and 50 mil diameter. And as we start to wind, we'll record the load in 1/4 mil increments until we reach 7.5 millimetres penetration, or we've reached full loading and the rear of the vehicle has moved up, so we can't penetrate any further. So as you can see, as we're winding the handle, the penetration gauge is moving clockwise, indicating there's some penetration, and the top gauge is showing increasing load.
Okay, so that was the Insitu CBR test. Okay, make use of the pickup, okay, to do the test on site. Okay, next one we're going to look at is a visual surveys. Okay, so the visual surveys, the project level visual surveys, which is a short-term survey, which for short-term work should be conducted on foot. Visual surveys from moving vehicles are not adequate for project level purpose. Okay, so if you even the windshield survey, you know, they can spot the potholes, all those things, you know, the cracks, but they are not intended for the project level, not for the treatment of the road in short term. Need to consider whether a sample of the section is sufficient to make engineering judgment, or whether the whole section should be surveyed in detail. Usually project level evaluation cover 100% section being investigated, that is the survey are continuous. So if it's a project level the pavement study, then you need to survey the whole road. Let's say the road could be a street could be 2 kilometers long, so it need to be done for the whole stretch, 100% of it. But if it's for the you could do a survey, you know, the network survey, but it's not intended for for the short term, but intended for the medium term to long term. You may not required to do the whole stretch. You might just do a part of it, a sample of it, okay, to determine. So because you need to for the medium term or long term, probably you're not just concentrating on one streak, or one rod. You need to do a lot of the rods, you pick some representative rod and then to do some stretch of it. So yeah, so project level you do 100%, but if it's on the network level, you will do the this visual inspection. You might not need to do all of it, all the whole length of the rod. You just do part of it. The results of the visual surveys are generally adequate for decision on routine and some preventive maintenance treatments. So the visual surveys, they've been done, and then they log into the record book, and then and then sometime I think then they can straight away enter into the computer as well. They got the software to record all the defects. They use, like in New Zealand, they use the RAM to record them. Now they actually is online, and they record straight away into the computer, and then the RAM software will connect with the other software to make decision. However, visual surveys alone are not sufficient to determine the details of major patching or rehabilitation. Okay, so certain patching, let's say if it's quite extensive, like sinking, quite extensive cracks, this one the visual survey may not be sufficient, because you don't know the what's the reason behind it. We're gonna decide by the what we can see, what we can see on site. So one of the main manuals used in Australia for visual pavement surveys is the National Association of Australian State Authorities, NASRA. This one is the previous name for the OSROD. Okay, this is a guide to the visual assessment of pavement conditions. Okay, it's quite old version, 1987. But they still use it. They actually, it shows the different type of defects, but they just have some sort of criteria. How do you classify the defects, whether it's just mild or medium or severe? Okay, so that you can record it in the logbook. So for example, this one, the distress type, the severity, you can just you have to do some there's some they got some guideline to how do you quantify it, how do you specify it, whether it's just a medium or mild, or just a mild, it's low or medium or high. Okay. Okay, recording forms for visual distress by visual surveys. Okay, I'm not going to talk so much about all these the recording forms. I just show some forms because actually, like it varies from country to country. Like in New Zealand, they use quite a lot of the recording through the using the RAM software. Okay, other country they use other software to do it. Okay, there is no single standard method or procedure for distress measurement and recording. In fact, these methods vary widely among the road authority. So there's no universal methods. all over the countries, you know, in Oceania, in New Zealand, in Australia, and in Asia, in other part in Europe, in Africa, in North America, South America. They have all the different methods. They have different procedure. Okay, most road authorities have developed their own system of distress survey procedure depending on their available resources, need, and network characteristic. So all the country, they have their own form. You know, this one I think it's somewhere in America. Okay. This one I think is in America as well. Okay, the different type of form. And this one I think is on Australia. So they have they record the defects on the rod. You know, this one is this is a plan of the stretch of rod, 0, 20, 40, 60, 80, 100. Then this is just the length, you know, the length width, and the shoulder as well. So they can measure. They can just describe they can just put in the defects on the sketch. NZTA also has their own forms for surface distress data collection form. So the NZTA, when they also can record the defects on the rod. You know, they have this form. I think actually they got a lot of forms. So I just get a few of them just for a sample. You know, this there's a Transit New Zealand, which is the predecessor of the NZTA. So the first form is about it's an inventory. You know, the rod names you have to put if you do the survey for that rods. You know, the rod names, and then the carriageway. This form 1, form 2. Okay. And then the rods, shoulder, surface water channel. You know, because these are the rod survey, the pavement survey. Sometimes it covers the roadside drain as well, and the shoulder as well, not only the pavement. And the pavement. Okay, I think there are other types. I didn't include all the forms for this one, the Transit New Zealand, which is used by the NZTA. Okay, so that were the visual survey, whether on foot or by vehicle, or the lab testing, the testing on site or on site, which is in situ or in the labs. Okay, so there are quite a few the testing of the rod surface, some defects on the rod, which cannot be done properly by visual inspection. Okay, so they need a sort of a specialized machinery to do it. Okay, so these things are the following condition parameters are best measured by automated means: the roughness, rutting, surface texture. Okay, this one mostly is the shape, you know, the roughness, the rutting, the surface texture. So this one, they could use a laser profiling machine or profilator to do the. They just run the vehicle and they can do the testing. Okay, and then we have the skid resistant of the rod. So how good the rod is to check the you know, the whether is there enough skid resistance on the rod. They need to check that. The strength of the rod as well. Okay, the strength, and the noise level. So they got different machine to test all these different aspects of the rod. Okay, let's look at the laser profiling of the rod surface. the beam that shine on the rod. Check the rod surface texture. So the 3-point system, they can check the rod depth. The rod is along the wheel track. Okay, so they can use this the profiling machine to push mount on the front of the pickup, and they can just run along. They can check the rutting, the surface texture, and the roughness of the rod. The next one is skid resistance of the rod. They have a machinery to do that as well.
Kevin Menchie's been driving trucks for most of his life.
A great way to see the country. I really enjoy myself doing it.
And now he's driving this truck for the New Zealand Transport Agency, one of only 2 in the world. Kitted out with all the latest technology, it's designed to check the state of our highways.
And we use that information then to decide on the priority about where we need to go out and resurface the road.
This is the skid assembly cabinet.
Inside a specially made bald tyre, water is poured in front of it to recreate a vehicle braking and skidding during an accident.
As the truck is driving down the road, the operator can lower these inside the cab, and this wheel will naturally try and straighten and measure the skid resistance of the roads.
Over the next few months, the NZTA's 2 trucks will cover 22,000 kilometres of the country's state highway. Each summer, the trucks are brought over from the United Kingdom, where they're constantly upgraded with new technology. At a cost of nearly $2 million a year, the NZTA says it's money well spent.
So we're seeing a reduction in wet road crashes on the highway over time.
It collects data in 15-kilometre blocks, but if the truck stops, then all that information's lost and must be redone. Travelling at speeds between 45 and 80 kilometres an hour, Kevin says he's copped a bit of flack from motorists.
On the one lane, they get stuck on us. We can't pull over and let them pass, so they think we're being a bit arrogant, but we're not.
So the NZTA's urging drivers to be patient, because after all, this truck could save your life.
Okay, so that is the skid, the machinery to measure the skid resistance. And for the strand, actually we have there are 2 type of methods, which is a deflect. We use a deflectometer, or there's another type which is called the Pavement beams. Okay, so apparently this the deflectometer is a more efficient type of measurement for the strand of the rod. So this is the machinery. There's something that is below the truck. Something is moving back and forth. You can measure the deflection. Okay, so these are the pavement survey methods. These are automated survey. To there's something that the visual they cannot do by visual survey, and so they need the this one, the automated methods to measure the rod condition. There are two type of measurements, the sort of what they call the to do the condition of the rod, to classify the rod condition. One is the International Roughness Index. It's some sort of, you know, the it's a standard or rating of the rods. Another one is a Pavement Condition Index. Okay, so the first one is the International Roughness Index IRI, developed by the World Bank in the 1980s. Okay, so IRI is used to define a characteristic of the longitudinal profile of a traveling wheel track and constitute a standardized roughness measurement. The commonly recommended units are meter per kilometer or millimeters per meter. Okay, so this is the World Bank method. So they measure they have units from 0 to 16. Okay, the units 0 to 16. So you can see that, you know, the one, you know, the when it's at higher end, which is not, the what condition is not good, you know, erosion, gullies, deep depression, you know, and then 10 to 12 frequent shallow depression, some deep. 6 to 8 is frequent minor depression. 2, like around 4 is about surface imperfection, and then like 0 and 2 are good, you know, for the airport runway and superhighway, like between 0 and 2. New pavement about 2 to 3. Older pavement can go up to 6, and maintain unpaved rod, it could go up from, you know, this rod has been maintained from, let's say, almost 4 to about 10. Damaged pavement can go up to 10 as well. The rough unpaved rod, it can go up anything, you know, the 8 to 16. Okay, so yeah, so these are scale, you know, if it can sort of identify the different this one mostly they have this you know, the automated machine to do the testing, you know. We have this what's that, the machine, the pickup, you know, the profilator, the skid machine, all those things, the strand machine, the deflectometer. So this is something another sort of another way to present it, you know. They also about this, you know, the highway, airport, new paved rod, all the damaged rod. And, yeah, I think it's the same as the previous one, just that it's presented on a different way. So yeah, so this is the international the roughness index. Okay, so all the rods, they can be identified as what is a number. They just classify with a number. The Pavement Condition Index, this is also they have some sort of point system, but it's sort of different from the International Roughness Index. The Pavement Condition Index is a numerical standards utilizing value range from 0 to 100. So this is opposite of the II. The lower number means that the condition is good. Higher number means that condition is bad. Whereas this one, the Pavement Condition Index, the lower number means good. The lower number means bad. The higher number means good, to describe the current condition of concrete and asphalt pavement. This rating system provides an accurate reporting of the pavement current condition, as well as data for predicting expected pavement needs years into the future. So they have this for the streak, they can read the streak a rod, whether it's from 0 to 100. Above 55 is good, good, and then very, and then 70 to 85 is very good, and 85 onwards is to 100 is excellent, and below 55 is fair, and this below 40 is poor, below 25 is very poor, and below 10 is fair. So actually the PCI, the pavement condition index, is the three factors, which is a distress type, distress severity, and distress quantity. So there'll be later we look at that, what are those things, the distress type, whether it's a cracking or what, rutting, or distress quantity usually is I think the traffic loading, and then how severe it is, how bad it is. So the custom PCI rating scale, so above the 70 is considered as adequate, 55 to 70 considered degraded, and below 55 is unsatisfactory. Okay, so this is the PCI method. Incidentally, there are some correlation between the IRI and the PCI. Okay, so I think there's some sort of correspond correlations between, both of them. They are, they're measuring about the rod condition. For this one, usually the international roughness index measured by the machine. Where is this one? The pavement condition index. They have this one. They use visual inspection. They go and check the cracks, all these things on the rod, usually by the visual inspection, and they come out with the PCI. What is the PCI for that? Whereas for the this one will be so I think the next page we talk about the what constitute to the roughness. Okay, the IRI, international roughness. So again, I need to point out that the units are different. It's not standardized. Just now the one we saw was 16, but this one this one is in US. They have units which is up to 6. Okay, some so but the thing is that what are the things that constitute to the roughness of the rod. So we got 4 components. The structure components, the structure components of the rod, which can contribute to roughness, and secondly is the cracking components, and the rutting components, and the environmental components. Okay, so because these are the contributing, when you look at the machine, when you do the to check the roughness of the rod, they used to have this as the strand, to measure the strand of the rod, the pavement strand. The strand, they use a deflectometer to check for the strand, the pavement strand of the rod. And the cracking components, I think they can use to check as well the laser profilator to check for any cracking on the rod. Okay, and the rutting components, they also use a laser the profilator can get rutting on the rod, and that's one actually a big component of it is due to the environmental component. The whether it's because of the surface is is rough because the wearing cost is rough because of the oxidation of the bitumen, or because of the cost of the water, water in the pavement, in the subgrade, and the erosion by other things, so there's the environmental aspect of it. If there's any cracking, because sometimes because of the high temperature, the high temperature on the rod surface, which can cause cracking, especially if you have the cemented material. It also can cause cracking because of the what's it called, the cycle of wetting and drying because of the freezing and thawing, and then there's the water inside because the water change from liquid to ice. It will expand and then cause some cracking. So there's the environmental components of it. So this one, the roughness, these are the contributing components. As you can see, the roughness here, the traffic loading, it will contribute, and the pavement strength, it will contribute to all this, contribute to the pavement structure deterioration, the rutting and cracking. Cracking will cracking, it could be due to the surface, this one traffic loading, or it could be due to environmental factor, sun, environmental factor, environmental components. It cause directly it can contribute to the roughness as well. Okay, so these are the roughness scale. What are the contributing things, the factors contribute to the roughness. Okay, so now we look at the effects of the maintenance and rehabilitation. Okay, we're coming to the end. We have looked through, I think in this chapter we looked through quite a lot about the defects. What are the defects, what are the causes, and how to remedy them. Okay, so so the maintenance and rehabilitations are the two principal treatments used to extend the pavement life. These treatments have two main effects. They immediately improve the pavement conditions. So if you do the maintenance, if you do the rehabilitation, it will immediately improve the condition. For instance, a slurry seal can eliminate most minor surface stress that affect the future rate of deterioration. For instance, crack sealing prevents water from entering the pavement structures and subgrade through open cracks, which slow future deterioration. So you maintain it, actually can slow down the deteriorations, so that it will bring the pavement to good condition again, and then before it will start to deteriorate again. Okay, so it will sort of slow down the deterioration. Okay, for example, if you don't do any maintenance or rehabilitation, the whole rod may get deteriorated, totally become unusable in, let's say, 10 years. But with the maintenance, you could do it. The rod, you can slow down the deterioration. You can probably extend another 10 years for good serviceability. In general, maintenance can slow the rate of deterioration by correcting small pavement defects before they can worsen and contribute to further defects. So beyond a certain point, however, defects become too large for correction by mere maintenance. At this point, rehabilitation can be used to effect a wholesale correction of a large number of relatively severe defects, which provide a step increase in pavement condition. So we look at this sketch here. So we have this The horizontal axis is the accumulated axle loads, is the traffic loading, and the vertical axis is the pavement conditions. So this is when it's a new road, it's a good condition. So we got 1, 2, 3. One is the pavement deteriorates more slowly because of the regular maintenance. So this one up to certain axle loads, that means it's measure this will be determined by the time as well. You design for the certain axle loading, how much axle, for example 1 times 10 to the power of 7, for example, we call it the equivalent standard axle, so which we're going to cover in highway 2. But it's it's time dependent. So at the earlier time you have less accumulated axle loads, and then further down the track you got more axle loads. So with time, or with the increasing amount of axle loads, the axle loading, this concept is similar to like the aircraft landing. So with time the amount of landing for the aircraft will increase. Maybe it's a certain, for 5,000 landing, 10,000 landings, and 20,000 landings. That means actually is accumulated. It will increase with time. So in this phase, like 1, the pavement, because you got the potholes, you can seal, you can patch it. You got cracks, you can seal it. If there's some rod defects, you can correct it straight away. It will slow down the deteriorations. At the point 2 here, first rehabilitation efforts brings the pavement to near its original condition. So the rehabilitation, it could be resurfacing with an asphalt overlay. You will overlay a layer of asphalt, 60 mm thick asphalt on top, and you make the road new again. Okay, so you can it will provide good serviceability for a few more years to go. So the second, it will go down again. It will continue. We do have this the maintenance is still ongoing, patching of the potholes, seal of the cracks. But at the point 3 here, a second rehabilitation efforts restores most of the pavement to original condition. So at the point when it's quite severe, you need to do another rehabilitation. In this case, this one is further down the track. The pavement condition is much worse than the first time, so it will need to it's more costly to bring it up to good serviceability. But probably it cannot bring up to the new condition, so it will be not as good as the first rehabilitation. And after that, it will, with times, it will bring the pavement to the end of the life. So it could be 20 years depending on the axle loads. Because if you have a lot of traffic, probably you got more axle loads, you can reach the design axle loads much quicker. So certain roads it may take about 15 years, certain roads might take about 20 years, certain roads less, the light traffic road might take much longer, like 25 years. Okay, also depend on the type of roads, whether it's flexible or the rigid. The concrete pavement the pavement condition will deteriorate much slower than the rigid pavement, and the asphalt will probably last much longer than the seal, the chip seal. So left alone, pavements will typically deteriorate over time at an ever increasing rate. Maintenance and rehabilitation can slow or reverse this deterioration. The degree to which this occur is dependent on type of maintenance or rehabilitation, as well as the timing of such action. Okay, in systematic, in general, and early and systematic maintenance and rehabilitation plan is the most cost-effective and results in greatest extension of useful pavement life. So maintenance actually is very important for the road. Just like you you buy a car and then you need to maintain it regularly. Okay, you cannot just you just don't bother to change the engine oil, you don't bother to service it, you don't bother to change the coolant, you don't bother to change the spark plug. If anything wrong, you just don't service it. So if you don't do service anything, you don't do maintenance on your vehicle, it will just the thing will just condemn. In after maybe 5 years, your car will totally it cannot be used anymore. So the same thing goes with the pavement. If you don't do any servicing, you just don't care, don't patch the potholes, don't seal the cracks, the pavement, it will just totally become unserviceable. Okay, so unserviceable, so it will totally because it's such a bad state that you cannot do any maintenance to bring it to, in that case you need to do the reconstruction. Okay, so for this example here, I think it's from Western Australia. So when it's totally, the rod is sort of condemned, in this one is 25 years, so you need to spend 300,000. 300,000, I think, is to bring it up to be used again. Okay, so no maintenance, I think this that is 600,000 per lens mile. So that means that for this the first reconstruction and second reconstruction. Okay, so in this span of 50 years, you need to spend that much for per lens, for just single lens, one lens and then 1 mile. Okay, 1 mile long, which is 1.6 kilometer. You need to spend that much if you want to operate the road. Okay, so that the vehicle can the road is can be used by the traffic. So you have to spend that much money without doing any maintenance. So this one, actually we measure, in this case for this road here, we measure by the pavement, the PCI, pavement condition index. Okay, so okay, so the effects of maintenance on the pavement life cycle. So if you maintain the road regularly, okay, so you have the sort of you have a bits by bits of the maintenance. You maintain it, and then what's BST, some sort of this is the overlay. Not really sure what's BST. Some sort of maintenance rehabilitation. Okay, rehabilitation, you have to step by steps, and then you have got overlay, and then you bring to good condition again, and then you do, and then you have so this are regular overlay. It can actually sustain the road for quite a long time, even beyond the time. At the end of the, let's say, you still can make that rod serviceable. You can still continue to use the rod. Whereas you see that, if you don't do it, you had the blur. This one, the fan line here is about the reconstruction. So actually, you comparatively speaking, you talking about the maintenance and then the non-maintenance, the lens per lens mile. You have to spend 600,000 for non-maintenance per lens mile. But if you maintenance, you only spend about less than half of it, like 276,000 per lens mile. So it's cheaper to maintain the rod regularly rather than just leave it to run. Okay, so that's almost the end. Just on this pavement, when you do the pavement maintenance, when you do the repairing of the rod, you have to do some temporary traffic management plans. Okay, so the road crews, they will need to be able to direct the traffic to have certain, they have some traffic even to divert the road, the cones on the side, and then they have all the traffic sign for temporary traffic management. Just show the thing. So the NZTA, they have this the code practice for temporary traffic management. Okay, so when they do the maintenance, they need to manage traffic. So the contractor, usually like the NZTA or the council, the organ transport, they sub it out the job to the contractor, to put like Food and Hogan or Downers or whoever, so they need to if they want to do some sort of maintenance, rehabilitation, overlay the rod, they want to reseal the rod, they need to apply for some this one for the temporary traffic management, so they need to be approved. And then okay, so so they need to have, these are the signboard that can be used. I don't have the whole thing. Everything is actually in that the link in the PowerPoint. So I just show some sample of the signboards that will be used for this temporary traffic management. Okay, these are the signboards to be used. Some of the signboards. These are just a sample, and then the legend for the diagrams. You have to provide the traffic management plans, temporary traffic management plans to the clients, to the council, to the NZTA for the approval. So these are the legends for the what they means. The cons, the con signs. Oh, this one it's a hazard area, manhole. And then these are some of the two-way, two-lanes road. If you want to cross the lanes, the two-way, two lanes, you have to, this are plan, how you're going to manage the plan. You have to there's somebody here need to direct the traffic to only one side can, the sign here, one side is go, one side, the other side stop. Can only have one direction of flow at a time. Or you could have the one way, two lanes divider, or two lanes road. So this a dual carriageway. So there's some diversion of road, the diversion, because some work been done here, so they need to provide the cons and then to direct the traffic. So this is the temporary. You have to put all the signboard on site as well to warn the road user. Sometimes they have this big truck, they got the arrow show, the if the sign, to the if the arrow sign to show how the vehicle should move. So these are the traffic management plan. Okay, if you want to read more, then I think you need to go to this website, which I don't want to go in. Okay, so this is about the pavement maintenance, pavement evaluation procedure for the roads. Okay, these are the last part of the road maintenance. Okay, thank you very much. Okay.